Chapter 13 is a rather short chapter. It only has 4 sections. So in this last section of chapter 13, we are going to look at a few applications of the stuff that we've learned about curves. Now, the book does go into a little bit more detail and goes a little bit deeper into this stuff because I don't want to really dwell on all the applications. I want to kind of keep moving. I'm not going to make this a very long one. I might actually make a separate video on Kepler's laws that it talks about in this section, but I haven't really determined whether I'm going to do that or not. In any case, that will be kind of optional just to give you an idea of how these things can go. But take a look at the stuff in the book, read through some of it. It's all kind of interesting stuff. But for now, I'm just going to kind of introduce some of the ideas of how we can apply all the stuff we've talked about with vector valued functions. Now, there are definitely other things that we can do with them, but we will be focusing mainly on using these vector value functions to describe movement through space. So we have our parameter t, and really this is why we actually use t as the parameter so often. T here is going to represent time, usually in the seconds, but whatever units we decide in the particular example. R of t will be a vector valued function, and I might have to actually start putting arrows over things in this section, just because we are going to be looking at the norms, the magnitudes of these things as functions themselves. So we'll go ahead and put an arrow over this. This will be the position of an object or a particle expressed as a vector value function. Now the derivative, so the derivative of this position vector is actually going to be let me put it this way. So the derivative of the position vector gives us two things. First of all, it tells us how fast that r is changing. In kind of I guess you could say it tells us how fast the magnitude is changing in a sense. But it also tells us the direction that the particle is moving. So what we actually get is what we call the velocity. And the velocity of something is not just the speed. It also includes the direction that the object is traveling. So this is the velocity vector. If we do want to just talk about the speed, we can look at the real valued function v of t, which is the magnitude of the velocity function. That's just going to be the speed of the particle, without taking into account what direction that particle is moving. We can even differentiate this function again, or in other words, say we're looking at the second derivative of r, or in this case the derivative of v. This is going to be another function. We're going to denote a of t. This is the acceleration. And note, this is another vector. You can accelerate in a different direction than you are moving. So you can say if you accelerate in the same direction as your velocity, you are actually speeding up. If you accelerate in the opposite direction, you're slowing down. If you're accelerating to one side or the other, you're turning. All those are incorporated in this acceleration function. It tells us all that we need to know about all of that. But all we're really doing here is looking at the derivatives and giving them additional names to correspond with how we want to think of them in an actual example. So let's actually work out a problem based off these terms. So here we're looking at problem 9. This is from section 13.4. The page it's on, if you want to look it up, it's on page 918. But we just have a particle that moves according to a particular position function, this r of t, and we're going to describe all the other information about it. So of course, first thing we do is differentiate. So v of t, the velocity, I'm going to keep putting those arrows over it for now. The velocity function, which is the derivative of the position function, we just have polynomials here, so this is relatively easy. We have 2t plus 1, then we have 2t minus 1, and then we have 3t squared. They want us to also find the acceleration, which is a derivative of that one. So it's v prime. Derivative 2t plus 1 is just 2. Derivative 2t minus 1 is still 2. And the derivative of 3t squared is 6t. Then finally, we want the speed function, which is just the magnitude of the velocity function. So we're taking the square root of the sum of these, or the sum of the squares of those, I should say. So we have 2t plus 1 squared plus 2t minus 1 squared plus 3t squared squared. We can go ahead and simplify this a little bit just by expanding things out. It won't really turn out to be the nicest thing ever, but at least we can make it a little bit nicer than what we have right now. If we go ahead and square 4t, if we square 2t plus 1, we get 4t squared plus 4t plus 1. If we square 2t minus 1, we get plus 4t squared minus 4t plus 1. And then finally, this becomes a 9t to the 4th. Of course, the nicest thing about this is that the 4t's actually cancel each other out. And so we can combine like terms. I'm going to go ahead and move the 4th power term to the front. We have 2 copies of 4t squared. So we have 8t squared. Then we have 2 1s, so we have a plus 2. This unfortunately does not factor very nicely, so we're just going to go ahead and leave it as it is. Our speed function here is just going to have a square root in it. And that's really all we can say about it. But let's go ahead and graph this thing. So recall, we're going to say R is our curve, and its components are t squared plus t squared minus t, and t cubed with a variable of t, and just going to pick negative 10 to 10 just to make it big enough. So right off the bat, it looks like there's a cusp here, but it actually does kind of just curve around there. It's a little hard to see without turning it. That's why I like actually using GeoGebra and being able to show it to you. It's maybe not the kind of curve you expected. But if we go ahead and actually let me make a slider. Alright, now we have a variable a that we can plug into our curve and get points on the curve. In fact, let's go ahead and plot the curve at a, or the point on the curve at a. It didn't show up, but that's just because our parameter was a little too far along. So actually, this curve actually grows pretty quickly. So I guess I'm going to only be able to look at a's between like -1 to 1. Yeah. Okay. And then I'm going to go ahead and put in my velocity vector. So this is I'm going to call it v. It's the vector that points from the point R of A with it, and then we add on the displacement of our velocity vector. And remember that had components of 2a plus 1, 2a minus 1, and 3a squared. And let me get actually so you can see it better. There we go. So it's pointing along the curve, or did I, maybe I mistyped something. Okay, I see what went wrong. When I initially defined my parametric curve, this should have been t squared minus t, not t squared minus 1. There we go. That's better. So now our curve actually looks a little bit nicer, actually. And our velocity vector does point along the curve in the direction that the curve is moving. Now we'll define our acceleration vector. And I should have called this something differently. I'm going to call this b instead, and it'll update all the other ones. But since the acceleration vector, I want to call it a. That's what we're going to do. So acceleration vector is still going to be a vector. Shouldn't put r of a. Should put r of b now, since I changed what variable I'm plugging in. I'm still going to make it based off our point A, capital A, and it's going to be that point. The terminal point is going to be that point plus our formula for our acceleration. Remember, our acceleration was 2, 2, then 6, 6b in this case. So it's going to be a vector that points off like that. So we have our acceleration there. So maybe I'll even give these colors. So let's make the acceleration a green color, and the velocity a red color. Kind of distinguish them from the curve. So the curve is in black, and then we have green and red for our two vectors. And notice, unlike what we had in the last section, the acceleration here is not a normal vector to the curve, which you might expect from the fact that all we did was take the second derivative. It was a lot easier than having to turn things into unit vectors, then differentiate the unit vectors, and then making them a unit vector again. All the stuff that we had to do for the normal vector, we don't really have to worry about here. But it is actually on the same side of the curve as the unit normal. The unit normal is actually going to be pointing off in that same direction, and the acceleration vector is actually always in the same plane as the tangent vector and the unit normal vector. The book actually gets a little bit more into that when it starts talking about the tangential and normal components of the acceleration vector. I'm not going to get into that. It's kind of a lot of computation to get the formulas, and we're not really going to make much use of them. But just be aware that the unit normal is always pointing on the same side of that curve, even in three-dimensional space. It's always going to be pointing out this way in that same plane as both the velocity and acceleration vectors. So that's kind of what I meant by the unit normal points in the direction that the curve is turning, because it literally is pointing kind of in the same direction as the acceleration, but just as a normal vector instead of as this other vector that may have whatever angle with the velocity vector. Alright, so let's actually do some stuff where we can actually do basically some physics. Because in most problems, if we already know the path of the particle, it's not too helpful to do this. I mean, yeah, okay, we can talk about velocity and all that. But most of the time that we actually do want to deal with velocity and acceleration is because we have some sort of information that allows us to already know either the velocity or the acceleration, or maybe both, or have some relationship between them. In fact, the most common situation is when we have a force. A force, you can define force however you want, but the main thing that we're going to be doing here is using Newton's second law, which how we're going to be using it, it says the force, which is actually a vector. Forces have a magnitude of how hard something is being pushed or pulled or whatever, and it has a direction. A push to one side is different from a push from another side. But the amount of force is going to cause an acceleration that's in the same direction as the force, but it's going to be modified in magnitude by the mass of the particle. More massive particles are going to cause less acceleration because the total product has to still equal the same force. So here, m is the mass of the particle. So if we know the forces that are on an object, we can then get the acceleration that the object should actually be experiencing, and then we can actually use integration to get to the position vector. Let's actually put that into practice and look at projectile motion. So let's actually draw a picture of what's going to be happening here. We have some projectile that's launching from the origin. We're just picking the origin here just to make it easier on ourselves. We could actually pick a different point if we want to. We just have to modify what we're going to do in kind. But that projectile is going to be launched off at some angle with some initial speed. So we have, let's say, an initial speed of v0, an angle of theta. So v0, we're going to call the initial speed. Then that particle, once it's been launched, we need to figure out what forces are going to be on that particle or that projectile to see where it ends up. Where does it go? Well, the only forces that are going to be involved here is gravity. Now, we could actually look at air resistance too. Just to keep it simpler on ourselves, we're just going to look at gravity. And most people can realize that we're going to have some sort of curve that looks like that. It's going to curve down until it hits whatever ground. And like I said, the only force is going to be gravity, and that gravity is going to be pointing downwards. It's going to be pointing towards the ground. The force due to gravity. And then the force due to gravity, like I said, it's pointing downwards. If we're using our x and y's like we normally do here, downwards is a negative j. Or the unit vector pointing downwards is negative j. So we're going to take negative j, and we're going to then multiply it by the magnitude of the force of gravity. That force is the mass times what's called the acceleration due to gravity. So here, g is acceleration due to gravity. Actually, let me go ahead and move this stuff down a little bit. Just move it down here. Now, okay, so the acceleration due to gravity, that does depend on what planet you're on, all that kind of stuff. And it actually depends a little bit on elevation as well, though usually that's not such a big effect when you're talking on the scale of planets. So the acceleration due to gravity is going to be approximately 9.8 meters per second squared, or it could also be 32 feet per second squared. Just different units here. And the book brings up the 9.8 one, but then in the problems it actually has some problems that deal with feet, so you might have to use the 32 as well. But the point here is that the magnitude of the force of gravity is always going to be downwards, so the minus j, and then it's going to have a magnitude of mass times the acceleration due to gravity. Of course, that is going to be equal to the mass times the acceleration vector. And really the mass here was not too important because we actually are looking at the acceleration. That's what we're caring about. So the acceleration is literally just going to be the acceleration due to gravity in a downwards direction. And the important thing is that this is a constant vector. So if we do integrate it, so we get the velocity vector, and this is actually going to depend on time now. It's going to be the integral of acceleration due to time. And so we end up getting a minus gt times j. Because remember, we just integrate both. We integrate the components separately. The component of I, we don't really have to do much because it's not there. The component of j, we integrate minus g, we get minus gt. Of course, we actually do need to worry about constants, though. And this constant here is a vector. It can have an I component, and it can have a j component. And we're going to have to figure out what that actual vector is. Especially since we're going to be integrating this again to get the position vector. So before we even do that, we want to figure out what this constant actually is. But the way we figure out constants normally when we integrate is we go ahead and plug in a value that we know. We know what happens when the particle begins. At time 0, we know the particle is the origin, though that's not actually involved here yet because we're not dealing with positions yet. We're dealing with the speed. But we do know the speed is going to be v naught, and we know the direction is given by theta. Obviously, it immediately starts changing direction due to gravity, but we know initially what its direction is. So if we go ahead and plug in 0, the minus gtj goes away, and we just get that vector c. So the vector c is actually the initial velocity, but we need to somehow relate the initial velocity to the initial speed and the initial direction. Let's actually get a little bit more space for this. So how do we... So we have our x direction, we have our velocity vector, we have an angle here. We want to figure out what is the actual vector that's involved here. What is the, you could say, the v with an arrow sub naught, where the speed here is v naught. So let's go ahead and put in our y as well. Well, we basically have to think about what happens if we project this down onto our axes. And we have to use a little bit of trigonometry here. This length down here on the x-axis, the projection that we get, if this is our angle theta, is going to be, well, let me just write it this way. So this is the adjacent, and this is the hypotenuse. So adjacent over hypotenuse is, well, our x component. You could say this is vx or something. Our x component over v naught. But that's a trig function. That adjacent over hypotenuse is specifically the cosine of theta. So that means our x component is v naught times cosine of theta. We can also find out, let's just go ahead and use this triangle here. This side over here and this side over here are going to be the same length. That's the opposite over the hypotenuse. But it's our y value over our hypotenuse. And this time, opposite over hypotenuse is the sine of theta. So Vy, our v component, is V naught times sine of theta. In other words, C, the vector C that we have on the opposite on the previous page, is just going to have components of V naught cosine theta, V naught sine theta. Which also means that V of t, since remember we're taking C and then we're also adding minus GTJ. Basically, we're subtracting GT from the y component. So I'm just going to go ahead and that should be a V. V naught cosine theta. Then we'll have V naught sine theta, and then subtract the GT. That's our vector. Or that's our velocity vector anyways. We are going to have to integrate this again to get the position vector, which just means that we integrate each of the components. So the integral of V naught cosine theta, well, all that is constant. V naught and theta do not change over time. So we just end up with that constant times t. Then we have the same kind of thing over here. V naught sine theta is a constant, so we have V naught sine theta times t, but then we have a t over here, so integral of t gives us a 1/2 t squared, but times that g that we have. And then we end up with another constant. Maybe we'll call this C2. We have to figure out what that C2 is. This one's actually a little easier than it was to find out what the first C was. Because if we go ahead and plug in 0, which again, all these go away because they all have a t multiplying them, we just get C2. But R0, that's the initial point that we start at. We start at the origin. We specifically chose that point to make this easy on us. C2 is just the 0 vector. This represents the 0 point. So our final answer here for the position is V naught cosine theta times t for our first component, V naught sine theta times t for our minus 1/2 GT squared for our second component. We can also go ahead and write these as parametric equations. So x is V naught cosine theta times t, and y is V naught sine theta times t minus 1/2 GT squared. And if you want to go further, you can actually go ahead and try to eliminate the parameter t. Basically take this equation for x, solve for t by just dividing by the V naught cosine theta. I mean, that's just a constant here. And then you can end up replacing the t's in the y, and you end up getting a quadratic. You get y equals some quadratic in terms of x. So you can already see here that the path that this particle is going to follow is a parabola. Of course, we are assuming here that we don't have any air resistance and all that kind of stuff. So if factoring in some other piece of information, wind, air resistance, all that kind of stuff, can make things not be a parabola. But in this idealized case, we do get a parabola as a result. Let's take these formulas that we just derived and use them to solve a problem. So here we have a rifle being shot, so that our projectile here is an actual bullet. We have an angle of elevation of 36 degrees. we do not know what the initial velocity is. In fact, the muzzle speed that they're asking for here is the initial speed. We want to know what is the initial speed if we can figure out some other information about the way the projectile moves. So it's asking us if the maximum height of the bullet is 1,600 feet, how fast did it come out of the gun? So we recall our formulas. We have x equals, we had, what was it, v naught cosine theta, theta here being 36 degrees, times time. Y equals v naught sine theta times time minus 1/2 gt squared. I'm going to leave them as just theta for now. When we actually go ahead and solve things, I'll go ahead and plug in 36 degrees. Now, how are we going to figure out this problem? Well, what they're asking for, what they give us is the maximum height. That's the maximum value for y. So we want to know what t corresponds to the maximum value for y. And that t is going to help us then find out the muzzle speed. So how do we find a maximum value, or how do we determine where the maximum value of a function is? We use calculus. We are going to take our formula for y, and we're going to differentiate with respect to t. Say dy dt. Now, of course, most of the stuff here doesn't depend on t. V naught, theta, and g are all constants. So this is a constant times t, so we just end up with the v naught sine theta from that. And then here we have a minus, well, not 1/2 anymore. The t squared is going to give us a 2t. So we'll have gt. Now you might recognize that was the y component of our velocity vector. So you could actually just went back to that formula as well. But the important thing here is that this is a maximum when the derivative, well, y is a maximum when the derivative becomes 0. So we're solving for t. Set this equal to 0, we solve for t. We can bring let's bring the gt over to the other side and divide by g. And we get t is v naught sine theta over g. Unfortunately, that doesn't tell us everything. We still have v naught in the formula, but at the very least we can go ahead and plug this into our formula for y. So our y at max is v naught sine theta times this t value of v naught sine theta over g minus 1/2 g times the square of v naught sine theta over g. And that value is supposed to be 1,600 feet. Now this looks kind of a mess, but keep in mind g is a constant, sine of theta is just sine of 36 degrees is a constant. We're solving this equation for v naught. And it actually is a very much nicer looking formula than you might imagine, because what do we have here? We have two v naughts, we have two sines, we have a g on the bottom. Here we have two v naughts, two sines, and then the g's will cancel to give us exactly one g on the bottom. So this is really one thing minus half of that same thing. Or in other words, this whole thing turns into half of v naught squared sine squared over g, and that's going to have to be 1,600 feet. If we go ahead and solve for v naught, we have v naught squared is 1,600. We end up having to multiply that by 2 for the 1/2. We multiply by g, and g is going to be 32 feet per second squared because we are working with feet. So we have multiply by 32. And then we have to divide by the sine, or the square of the sine of 36 degrees. Go ahead and plug that into a calculator, because why not? We get 296,389. And if you want units on that, keep in mind 1600 is in feet, 32 is in feet per second squared, so we end up with feet squared per second squared, which might seem like a weird unit, but that's because this is not the muzzle velocity, but the square of it. We need to take the square root of this as well. So V naught, the square root of this thing, is going to be 544 feet per second. And that's the answer. That's what we were looking for. So this is one of the ways we can actually make use of all this stuff. Of course, we haven't really taken as much advantage of the power of vectors as we could. That is what the book gets into when it starts talking about the Kepler's laws and the law of gravity and all that kind of stuff. And it actually uses vectors to show that the orbit of a planet around the sun is in fact an ellipse. And it does it just straight up deriving the particular equation of the orbit of a planet. It does get a little bit complex. There's a lot of steps involved. It's not the easiest thing, but without vectors, it'd be way worse than it is here. But I'm going to leave that for you to look up in the book, and I'm going to go ahead and stop the video here. So I'll see you guys in the next section.